I get this all the time. Hey, I built my LLM, but it's running out of memory. It's painfully slow, and the response time is terrible. Sounds familiar? You're not alone. The truth is, optimizing large language models is hard. But in this video, we're gonna make it simple for you. We break down the top 10 optimization techniques that you can apply onto your LLM to make it faster, more efficient, and a whole lot cheaper to run. Whether you're fine tuning a model or deploying it in production, these tips will save you time, money, and headache. Let's dive in. But before we look at top 10 strategies, let's try to look at what are the core bottlenecks and inefficiencies when it comes to large language models. So the first one is that large language models have higher computational cost. What it means is that they require a lot of metrics manipulation, and because of that, generally have like a very high latency as well as high power consumption. They also require higher memory access because large language model, like let's say if you are writing a prompt, for every single word in the prompt or every single token in the prompt, you have to run attention for each of them. Also, there is a higher memory cost because you have to load the model weights every single time due to run attention. So these all things makes optimization of LLM much more important. Very briefly, let's look at how LLMs actually work.
You read the literature, or you read super technical documents. First is tokenization. Each model will have its own tokenizer. And the thing to think about when you think of tokenizers, when they did pre-training, they downloaded the internet and some, right? And they cleaned it up, etc., etc. So a tokenizer, they tried to get what is the minimal set of character groups that can represent this entire training data set efficiently. So I tokenize, the LLM understands it. I go into this thing called prefill. Prefill is the stage where you compute the attention mechanism. And then I start generating tokens one at a time. The red and the green just signify, hey, I'm storing those tokens on the GPU. The green is the latest one that I sent out.
Now you might be thinking, what is the actual data that sits on the GPU? First, token is approximately 4 characters. So from here I have two vectors. So the first vector is just showing token 1 to token v, where v is the total number of tokens that I have in my tokenizer. The second vector below is just some numeric index. I don't want to query by a tokenizer every single time, so I have the IDs associated with it. My job is to convert whatever the text that or prompt that comes in, is to convert that into vector of token IDs. Tokens have corresponding embedding vectors. Embedding vectors could be anything. We have videos, images, text, or tokens, anything. Think of it as a representation which LLM can use to compare things or do maths on. That's why we want to convert it into some vector representation. From those token IDs, I went to actual embedding vector itself. So if you look, make me sound rich now becomes a matrix. Sound richer becomes a matrix in another column. So you are really putting this large matrix on the GPU. Next question you can ask is, why GPUs? Because GPUs actually process these matrices very, very fast. So this is what the formula for attention mechanism looks like. So this is the input vector, which is your prompt. And then there is query vectors, key, and a value. So query vector is just new token in the decoder stage. Key is basically the entire sequence, as well as value is the weighted sum of our previous context over the entire sequence. So initially what we do is we take the query vector and then multiply it by the key, transpose of the key. This multiplication, then we apply softmax to it and then do a weighted sum over it. So this one thing to notice here is that the key vector and the value vector, they don't change for each word. In fact, they are calculated for the entire sequence. So that's but the query vector actually changes quite often. So there is a cross matrix to query matrix to vector multiplication here that happens for each word. For the optimization techniques, there are 3 areas where you can apply the optimization techniques: at data level, model level, as well as inference optimizations. Data level optimizations are nothing but optimizing the prompt Model level optimizations are optimizing the architecture of the model, and inference level optimizations are optimizing GPU access or inference time computations. Great. So now we understand the attention mechanism in LLM. We understand the two phases of LLM, profiling and decoding. And we understand that there are matrix multiplications involved here, which are very, very heavy. So now we are shifting gears, we are moving towards the optimization techniques. So let's look at the top 10 optimization techniques that you can apply to make your LLMs more effective, more faster, and more cheaper. At number 10, I'll say skeleton of thought. So what the idea here is that there is a skeleton stage. So when you ask a question to ChatGPT, it actually identifies certain keywords in the response. So in this case, let's say the question is, what are the typical types of Chinese dishes? So it generated all the list for you: noodles, hot pot, rice, and whatever. And then in the point expanding stage, what it does is basically takes all the skeleton that it has generated and add context to it to make it more verbose and to make it more readable. AV cache is another. So you have a lot of matrix multiplication here with multiple attention heads for each model. So in this case, there are three metrics: query, key, and value. As we discussed earlier, query represents the vector here, which is the vector of last word. Key and value remains the same for the entire sequence. So when we do the attention mechanism, some of these values can be cached easily in the key value cache or KV cache for faster lookup. As we discussed in the last video about Llama 4 architecture, Llama 4 uses a very efficient feed forward network design, which is called mixture of expert. So in dense models, what happens is you have, for each step, you need to have all the parameters. One case of mixture of expert models, you are actually building expert with very limited set of parameters. So each expert could have different set of parameters, and all of them are performing different operations or different tasks. Router takes care of managing these exports, and then at the end, all of these exports are again combined to generate the attention. And this is a model optimization technique. As the name suggests, multi-query attention means that we use multiple queries, but we share same keys and value across multiple attention heads. In the figure, the center one is multi-query attention. There is also grouped query attention, where you have grouped some of these queries together. And there is also kernel based attention. So right now we are using softmax as we saw in the example earlier, but you can also use kernel based optimization techniques, which makes the quadratic calls linear. Quantization in large language models is a technique that reduces the precision of the model's weight and activations, effectively shrinking the model size and improving inference speed. This is achieved by mapping high precision values like 32-bit floating point to lower precision like 8-bit integers. PEFT, or parameter efficient fine tuning, is a family of techniques that adapt large language models to a new task by tuning only a small subset of parameters instead of the entire model. So these makes it like really fast to fine tune. You must have heard LoRa, which is implementation of PEFT. So LoRa inserts small tractable metrics into the attention or feed forward layers. These metrics are low ranks, meaning they can have fewer parameters but still can effectively capture the task specific adaptations. As the name suggests, LoRa means low rank adaptation. Original model weights are frozen, only the lower LoRa weights are trained. And if we integrate quantization with LoRa, it becomes QLoRa. Flash attention and flash decoding are inference optimization techniques. Mostly we are optimizing graphs here. So flash attention fuses the entire attention operation into single GPU kernel, splits KKV into blocks, thereby accessing only limited data in memory. Kernel fusion combines multiple GPU operations into a single GPU operation. This is popular optimization techniques used in some of the tools like DeepSpeed and VLLM. Instead of computing KQV, K and Q and then V separately and writing each of them into memory, you compute KQV in one pass. As an example of that, it could be flash decoding, where flash decoding enables parallelism across the sequential dimension, not just batch. Distillation is another important technique. Here we use two models, teacher model and a student model. A pre-trained teacher model transfers its knowledge to a smaller, more efficient student model. This process allows the student model to achieve similar performance to the teacher model while requiring less computational resource and memory. The student model is trained using the teacher's prediction or other representation of a training symbol. Another important one is linear operator optimization. So this is generally used in attention layer where you have KQV. Q is your vector. It can also be used in feed-forward neural network. So in the transformation block, they are typically implemented using GEM, which is the general matrix multiplication. But during decoding, Q becomes a vector, leading to GEMV scenario, which is the matrix vector scenario. There is a library, open source library for it called TensorRT. This was introduced to improve the GEMV kernel to, to improve decoding performance. And this is speculative decoding is a clever technique that makes autoregressive model generate text at a faster rate. So instead of generating one token at a time, speculative decoding tries to guess ahead multiple tokens using lightweight model and then verifies those guesses using a full-sized LLM. So there are two stages here. Draft construction, where you use a smaller model, a draft model, like a distilled version or a quantized version of the large language model to predict multiple next tokens. And once these tokens are generated, we actually verify those tokens using the full target LLM to compute probabilities of those draft tokens in one pass. Then there is pipeline parallelism, where you shard the model into chunks where each chunk comprises of a subset of layers that is executed on a separate device. And once these results are generated, you actually combine the results. There is also tensor parallelism, which involves sharding individual layers of the model into smaller independent blocks for computation. So this is much more on a granular level. These are some of the optimization techniques that everyone should be aware of when they are fine-tuning or building a large language model. I think I covered most of it. If you guys felt like that I missed something, please let me know in the comments. Hope you guys liked the video. Hope you guys enjoyed the video. And yeah, I will see you in the next video.